Hello everyone. In the last few classes, we discussed about the plasma optics, different modes of oscillation in plasma such as the longitudinal or transverse oscillations. Today, we will discuss what is plasmon and how we can detect the presence of plasmons using some experimental methods. So, a plasma oscillations in a metal is a collective longitudinal excitation of conduction electron gas. So a plasmon can be defined as a quanta of plasma oscillations. We can excite a plasmon by passing an electron through a thin metal film like this, and so that it reflected, the electrons will be reflected or it can be transmitted through this medium. The energy loss which is occurring during this transmission or reflection is equal to the integral multiple of plasma energy. So the total energy loss is equal to plasmon energy. So in these figures, we can show the creation of plasmon, schematically represent the creation of plasmon in a metal by an inelastic scattering of electrons. So this is our incident electron. So it will create, it is passing or reflected or scattered through this thin metal film, so that the scattered electron will lose energy. Correspondingly, there will be a formation of plasmons. It can be occur in a different way, where an incident electron can create two plasmons, and there will be loss of energy for the electrons, so scattered electrons. There are certain conditions such as the incident electron should have energy of the order of 1 to 10 kilo electron volt, whereas the plasmon energy will be of the order of 10 electron volt. This slide you can see an experimental setup which uses a spectrometer with an electrostatic analyzer for the study of the presence of plasmons through electron energy loss. The figure, this is the schematic of the experimental setup. Here, the electrons created in the cathode is passes through a monochromator. The purpose of the monochromator is to confine the electron beam which is passing through the which is then passing to the metallic specimen. So it will form a beam of electrons when it passes through the monochromator. The beam of electrons interact with the electrons in the specimen. So this is the metallic specimens where the plasmons will be formed. The scattered electrons from this metallic specimen will be of high energy. So there will be a retarding field here which is used to which is used to control the electron beam which is emitted from this scattered from the metallic specimen, which is of high energy. So this film, this retarding field which controls the electrons, which is then passes to a spherical condenser. This will be containing different lenses, so that the beam is then which will be guided into a multiplier unit which counts the electrons. So this will be attached to a spectrometer, which is a magnetic field based spectrometer, which can measure the electron energy loss which is happening when it is scattered through this particular metallic specimen. This is the typical energy loss spectra for electrons which is transmitted through the metallic films. So this is for aluminum metals where we can see there are different peaks. So this is different. There are actually 12 loss peaks for aluminum, and if you are considering magnesium, there will be 10 loss peaks. So there will be 10 of these peaks in the case of magnesium. So this is for aluminum. Here for the aluminum, you can observe combinations of 10.3 electron volt and a 15.3 electron volt doses at different energy levels. So this is corresponds to the energy corresponds to 10.3 electron volt is the surface plasmon, which is due to the formation of surface plasmons in metals, and this is the highest peak energy which is due to the volume plasmon. So that is well inside the metals there will be generation of plasmons. So that is called the volume plasmons. So the corresponding energy is 15.3 electron volt, whereas surface plasmon energy is 10.3 electron volt. You can see that this energy this is repeated at regular intervals. So this is keeps repeated. So the peak of this one will be keeps repeating at different levels. So this is 15.3, then about 13.6, like that. So all these peaks are within the energy levels, that is between 0 to 100 electron volt, which is a low loss region. The energy loss peak is which is due to the plasmon excitations through the excited primary electrons. Similarly, if you consider the similar loss peaks for magnesiums, this will be a combinations of 7.1 electron volt, which is for the surface plasmon energy, and 10.6 electron volt, which is corresponds to the volume plasmons. So this will be different for different metals. Hence, we can conclude that the position or width of the peaks depending on the electronic structure of the metal. So this will be different for different metals. So this particular table shows the volume plasmon energy in electron volt for different metals as well as for dielectrics. So as we seen earlier, this is for aluminum it is 15.3, and for magnesium it is 10.6 electron volt. This is the corresponding calculated value which we can calculate it using h cross omega p, so or h cross omega cap. So here you can see that, so this is well in agreement. So the observed values of this this volume plasmons and as well as the calculated values are well in agreements. There is only some minor difference between these two values. All these things shows that there is a generation of surface plasmons, and the energy loss peak is due to the plasmon excitation, which is through the excitation of the primary electrons. The position or width of the peaks depending on the different metals. So that is means that depends on the basic electronic structure of the element which is under study. Hence, we can conclude that the plasmons are generated through the excitation of electrons, and the plasmon energy is discrete. So we can have energies in the form of discrete values. The quantum of that energy values are called the plasmons. So, okay, thank you.